Welcome back to our final lecture in our wetland hydrology series. Our learning objective for this segment is to describe the ways in which wetlands can improve water quality and calculate a theoretical reduction in nutrient concentrations. While not all functions may be present in all wetlands, wetlands can work to improve water quality through multiple mechanisms, as summarized in this illustration. These processes include sedimentation, removal by bacteria, adsorption and filtration by roots and stems, ion exchange and absorption by sediments, and uptake by vegetation. We know from our stream unit that slower moving water has less capacity to transport sediment, so if we slow the water down in a wetland environment, there is an opportunity for all of the particulates that are being carried to settle out. In addition, wetland vegetation can help with this process by helping to filter particulates from the water as it moves slowly past the sticky roots and stems of wetland vegetation. Wetland vegetation provides two other important functions. Vegetation requires essential nutrients like nitrogen and phosphorus to grow. So they are taking these nutrients from the water and sediment, and at least temporarily removing them from the environment. I say temporarily because around here, most wetland plants will senesce at the end of the growing season, and as this plant matter decays and decomposes, it can release the accumulated nutrients back to the environment. That is why harvest of wetland vegetation can be an important management technique in some managed systems. Another function of wetland plants is that they can provide oxygen to the root zone. The wetland sediments will be anaerobic normally because all of the pore space is filled with water. But we learned previously that some hydrophytic vegetation is specially adapted to bring oxygen to the root zone. This can have important implications for chemical reactions taking place in the wetland sediments. Microorganisms in the wetland environment can have important functions for breaking down and reducing contaminants. For example, the illustration here is showing the nitrogen cycle. Denitrifying bacteria that convert nitrate to dinitrogen gas thrive in anaerobic environments and can be an important water quality concern in agricultural wetlands in Indiana. Finally, the wetland sediments also have an important role. They can help with filtration if there is significant flow through the sediment pore spaces. In addition, some chemicals can be trapped in the sediments by adsorption. Adsorption refers to the adhesion of a chemical species onto the surface of particles. Some pesticides can adhere to wetland sediments and plants. Finally, some chemicals can bond with the negatively charged clay ions in wetland sediments, taking them out of circulation. Although there are different processes going on to improve water quality in a wetland environment, all of these processes are concentration mediated. That is, the potential for further reduction is controlled by the inflow concentration of a chemical into the wetland. Therefore, it is common practice to provide a rough estimate of the potential decrease in concentration in the wetland environment using a first-order chemical decay equation. In this case, the net impact of all of the wetland functions, sedimentation, plant uptake, microorganisms, etc., are represented by the aerial removal rate constant, K, which shows up in the equation here. This equation shows us that the outflow concentration, C0, is equal to the inflow concentration, here, Ci, times this exponential function raised to the power of the aerial rate constant divided by the hydraulic loading rate. Ka should be specific to each wetland environment being studied. The background concentration, Cb, recognizes that some chemical contaminants are naturally occurring, and it is not possible for a wetland to reduce the concentration below this background rate. Note the time units on Ka and Qd, the daily inflow rate, need to be the same in order to cancel. As you can see in this ratio here, or in this ratio here. The hydraulic loading rate is essentially just normalizing the mean daily inflow rate by the wetland surface area in order to estimate the depth of water being added to the wetland per day. So QLHR equals QD, which is equal to the daily inflow rate, divided by the wetland surface area, A. Both the background concentration and the aerial removal rate will depend on the specific wetland being studied. But this table from your textbook gives a rough idea of some average parameter values. Remember, to convert Ka from meters per year to meters per day, just divide by 365 days per year. Also note that 1 gram per cubic meter is the equivalent to 1 milligram per liter. Let's do an example. If a nearby wetland has an average total phosphorus concentration in the inflow of 0.5 grams per cubic meter, what is the potential outflow concentration if the wetland has a hydraulic loading rate of 0.1 meters per day? We know that we will use our exponential decay equation, and we are given that the hydraulic loading rate is 0.1 meters per day, and the inflow concentration is 0.5 grams per cubic meter. From the table, we can assume a background concentration of 0.02 grams per cubic meter, and the aerial removal constant is 12 meters per year. So for our solution, the outflow concentration minus background is equal to the inflow minus background, 0.5 minus 0.02, times the exponential function to the power of Ka divided by the hydraulic loading rate. Please note that since the loading rate was given per day, we need to multiply it by the number of days per year in order for the units to cancel out. The units of the exponent must cancel so that the exponent is unitless for this to work correctly. With that conversion, our exponent is negative 0.329, and our final outflow concentration is 0.365 grams per cubic meter. I would like to review one last thing with this equation. It can also be turned around to use it to solve for the area needed for a target concentration reduction. First, we substitute in that the hydraulic loading rate is the daily inflow divided by wetland area here, and that brings area into our equation. By taking the logarithm of each side, we can solve for the wetland area. And so here we have an expression for a target area as a function of a target outflow concentration. This concludes part 4 of our wetland unit. You can now use the Wetland Policy Quizlet to explore the time history of wetland regulation in the U.S. We will get additional practice with these calculations during our Unit 9 in-class activity.